All right. So all the resistors will have the same voltage drop across each and every one of them. The current is going to split into branches. The total current supplied by the battery will be the same as the individual currents added together. So this is the conservation of charge. All right, pick out the best answer.
B.
B.
All right, so the overall resistance is going to go down. All right, so those of you guys who said B, give yourselves 5 points. The rest of you guys who picked B, give yourselves 2. Problem number 1, problem number 2, these are too simplistic, so I'm not going to worry about it. Problem number 3 is just as simple. Except now you got the resistors in terms of the parallel and series in combinations. Okay, so how would you do a problem like this? What's your starting point? All right, ignore the numbers, just tell me what to do.
You combine the ones on the right first because they're in.
All right, so combine these two. They're in series. All right, so if they're in series, what do we do? Add them up.
Yeah.
And then, all right, so those two will become parallel to this one, right? And then, so what do? We add them up inversely, reciprocally, and then what happens? Now this one is going to be in series with the total resistance on this side. Now we have to add them up again. So combine these two into a single one. So this is the total resistance on the right-hand side. They are in series, so which means that you have to add them up. These two will be in parallel. How do you know that they're going to be in parallel? Because they will have, there's junction points here, so the current is going to split. So you will have to add them up reciprocally. All right, so it's going to give you the total resistance on this side. At this point, it's going to be the same current going through both of them, so which means that they will be in series, so which means that you have to add them up. So they're additive, so this is what you end up getting. All right, so this sort of stuff is straightforward. This is high school to this point, so it's not that complicated. We talked about the household appliances. All right, pick out the best answer. We talked about this last time. So D is going to be the best answer. Give yourself 2 points. Household appliances are connected in parallel, so you can turn on and off the appliances without shutting down the circuit. If they're connected in series, every time you would turn something on, you would be shutting down the entire circuit. All right, so D is the best answer. All right, so far, everything that we've done today is high school physics. It's not very realistic. The real circuits are complicated, kind of like this. All right. So if you have a circuit which has a lot of voltage sources and a lot of resistors connected in parallel, series, or whatever, how do you do a problem like that? Kind of like this. This is the car's wiring system that you're looking at. All right, let's just go over this real fast so you guys could visualize it. Number 1, you got the battery. So the cars will have a 12-volt battery. So what does the battery do? It's going to generate a current. And then this is the current which is going through the headlights in this case. The headlights are offering quite a bit of resistance, which is kind of cute. And then the rest of the current is actually going through the alternator. It's just charging up the alternator. All right, so you got the battery, you turn on the ignition. So the current is going to go through the battery, and it's also going to go through the alternator. So what does the alternator do? It's going to charge up the battery in return. All right, so you got the battery, you got the alternator, you got the headlights. All right, notice that you got 2 voltage sources. One is the alternator, the other one is the battery. So what is the amount of current coming out of the battery? Battery is going to offer a little bit of resistance because of the corrosion. And then you have the alternator, it's got its own wires. Wires will offer a little bit of resistance, so you can see how much of a resistance that they will offer. And definitely the headlights will offer a lot of resistance so that you can turn this current into light, beaming light. All right, so given the fact that the current is going to split at point B, you got your junction point right there. All right, so how much of the current do you think is coming out of the battery and going to junction B? How much of the current is going through the alternator? And how much of the current is going through the headlights? All right, notice that you can measure the resistance values for the resistance of the battery, the wires connected to the alternator, and you may even know the resistance value of the headlights. But what is the amount of current going through the headlights? What's the amount of current coming out of the battery? What is the amount of current coming out of the alternator? How do you calculate that? When you apply the high school physics, and that's exactly what we've been dealing with so far, which is what it is that you guys know in terms of calculating resistors in parallel or series, it's not going to work out. This stuff gets kind of complicated. How many unknowns do you have? 3. How many equations do you need in order to solve for 3 unknowns? At least 3 equations. You can have 4, 5, 6, but you need to have at least 3 equations. So how do you generate 3 equations in order to solve for 3 unknowns? All right, so for complicated circuits, when I say complicated, it's somewhat complicated. This is really not that complicated. This guy named Kirchhoff if you're taking high school physics, or Kirchhoff if you want to be a little bit more formal, or Kirchhoff if you're German, offer some rules. These are known as Kirchhoff's rules, or Kirchhoff's rules, or Kirchhoff's rules, depending on who your instructor is. This guy is German, and he came up with some interesting rules that we will get to apply. Okay, so those of you guys who are getting into electrical engineering, and most of you guys will still have to take circuits if you're an engineering major. Okay, so Kirchhoff's rules are the ones that they will get to apply, and then there are a little bit more nifty rules as well that they will mention. Okay, for circuits which are somewhat complicated, not entirely complicated, but somewhat complicated. All right, so this guy came up with some rules. So let's talk about his rules. Let's talk about his rules. All right, open up chapter 19. Lecture notes. All right, so I did the simple derivations for these. And derivation DC circuits. I think that evidently when I was digitizing this, I wasn't following a particular order. Pages are randomly placed. Okay, so find this. It says Kirchhoff's rules. This is what we need. Okay, so it's got two rules. One of them is called the loop rule or the voltage rule. All right, so you got the loop rule, depending upon the book. The second one is known as the junction rule. All right, the first one is the Kirchhoff's loop rule, or it's known as the Kirchhoff's voltage rule. All right, so this means voltage. All right, you may end up seeing both of them depending upon the book. All right. All right, so I'm trying to figure out how best to explain it. All right, so the loop is going this way, the current is going this way, there's got to be a voltage drop. Okay, if I say it that way, you guys will go to hell. You're not going to get that. All right, we got the derivations, the lecture notes, the solutions. Okay, instead, I should do something a little bit different. I want to illustrate something. Okay, so I'm going to use problem number 5 as a setup so you guys know what I'm talking about. All right, the first one is called the loop rule, which means that I'm going to take a look at the voltage gain and the voltage drop across each and every single resistor in a given direction. So I'm going to loop around the circuit. Loop rule simply means that I'm going to start at this point and I'm going to loop around in this direction. This is my loop. Notice that this is a clockwise loop. And then I'm going to check to see if there's a voltage gain or voltage drop here. I'm going to check to see if there's a voltage gain or voltage drop here. I'm going to do the same thing, voltage gain and voltage drop, voltage gain and voltage drop. So which means that as I'm looping in this direction, I'm going to do an accounting. I'm going to check to see if there's a voltage gain or voltage drop. All right, guys. When the current is going across a resistor, there's always going to be a voltage drop. So the energy is going to be lost here. All right, across a resistor, just hear me out first, and then we'll do the formula. Current going through a resistor, which means that the electrical energy is going to get converted into heat and light. Now the current now is going to go through a battery. Okay, now the problem here is current is moving in this direction, in the direction of the loop. All right, so my loop is moving in this direction. The loop is going from a higher voltage towards the lower voltage, which means that in the direction that I'm drawing my loop, there's going to be a voltage drop. So there's going to be a voltage drop across the resistor. There's going to be a voltage drop across the battery. The reason why this is happening is because in the direction of the loop, this is going to experience a voltage drop. You go from higher altitude towards the lower altitude. You're going from a higher voltage towards the lower voltage, which means a voltage drop. Regardless of what happens, in the direction of the loop, if you're going across a resistor, if the current is moving in the same direction, there's going to be a voltage drop. Now you hit this battery. Notice that you go from a lower voltage towards the higher voltage, so there's going to be a voltage gain. All right, voltage drop, voltage drop, voltage drop, and there's going to be a voltage gain. Okay, so the rules that we will discuss, when I say in the direction of the loop, this means that my loop is moving from left to right, and the current is also moving in the same direction. So we will check to see which direction the current is moving in reference to the direction of the loop. All right, so you will have to look at the direction of the current, and then you have to look at the direction of the loop. Are they in the same direction or in the opposite directions? Guys, this country being free, all right, it's your constitutional right to draw the loop either in the clockwise direction or in the counterclockwise direction. All right, it doesn't matter which direction you want to draw. It's up to you. What's important is make sure that you keep track of the direction of the loop with respect to the direction of the current. Make sure that you're consistent. Okay, that's the only requirement that you have. All right, so now let's get back to the rules. All right, so when I say loop, this is the direction of the loop, and notice that the current is in the same direction. Loop and the current in the same direction. Across a resistor, voltage drop. That's a rule. Got it? If the loop and the current, they're in the same direction across a resistor, it's going to be a voltage drop. If the loop and the current are in opposite directions, voltage gain. All right, so these are the rules. If your loop and the current in the same direction, voltage drop across the resistor. If the loop and the current are in opposite directions across the resistor, there's going to be a voltage gain. If the loop going across a battery, if it jumps from a higher voltage towards the lower voltage, if it's pointing from a higher voltage towards the lower voltage, there's going to be a voltage drop. If the loop is going from, it's pointing from lower voltage towards the high voltage. Notice that I changed the direction of the loop in this case. Loop is pointing from lower voltage to the higher voltage, there's going to be a voltage gain. Okay, so these are the rules. Loop and current in the same direction across the resistor, voltage drop. All right, so the loop and the current pointing in opposite directions across the resistor, voltage gain. Loop pointing from a higher voltage towards the lower voltage, voltage drop. Loop pointing from lower voltage towards the higher voltage, voltage gain. Okay, guys, this is known as the electromotive force, which is the same as voltage. All right, so this is the symbol for voltage, electromotive force. Voltage is a modern name. The electromotive force is a concept that they came up with because they didn't know what was driving the current. So the lack of understanding meant that there was some kind of an electromotive force responsible for driving the current. The modern name is voltage. All right, so that symbol means voltage drop, electromotive force. They mean the same thing. Okay, so now let's do this problem. Okay, this is a simplistic enough problem. I'm gonna do my loop in this direction. All right, so that's the direction the loop is gonna have. I'm gonna start at point A, boom, boom, boom. This is the direction that the loop is gonna go. So let me just indicate the direction of the loop. All right, so I'm looping in this direction. This is cute. This is too bad. All right, I decided to, this is my loop. I'm looping in that direction, clockwise direction. I want you to notice that the current is also in the clockwise direction. So the current is also flowing in the same direction. So they're moving in the same direction. All right, so what's gonna happen? There's gonna be a voltage drop here. And notice that the loop points from higher voltage towards lower voltage across the battery. There's gonna be a voltage drop. Here, there's gonna be a voltage drop. Here, the current and the loop, they're in the same direction. There's a voltage drop here. And notice that now the loop points from a negative towards the positive terminal, and there's going to be a voltage gain there. All right, so you get a voltage drop, voltage drop, voltage drop, and then you get a voltage gain. All right, I don't like using numbers. I'm not like you guys. It's a waste of time. So I'm just going to resort to symbols. Symbols tend to be much cleaner. When you guys get more advanced in your studies, you will appreciate the symbols better. You can always plug in the numbers later. Numbers just make it way too complicated. It makes it really messy. All right, so I'm gonna call this the first resistor, R1. This is my first voltage source. I'm using epsilon 1. Traditionally, that's what we use instead of V. This is my second resistor. And this is my second voltage source. Okay, now it's cleaner. All right, so I want you to notice that we got values for the resistances. We also have values for the voltage sources. So obviously, the only thing we don't know is the current, right? So how do you find the current for a system like that? This is simple enough. It's straightforward enough. So let's tackle that problem. Okay, so we will get to use the Kirchhoff's voltage rule or the loop rule. So what do I know? I'm going to start right at this point. This is my starting point. All right, so I'm going to do my calculations across the resistor, across the first voltage source, across the second resistor, and across the second voltage source. And I'm going to loop back to that point. So we will start from here, and then we will just tally up everything that happens. All right, so across the first resistor, there's going to be a voltage drop. So the current going across the first one is going to experience a voltage drop. All right, so this is this. We just did this. All right, across the battery. All right, so the loop is pointing from a higher voltage towards the lower voltage. So what that means is there's going to be a voltage drop. All right, so this voltage drop represents what happens here. And then now we are here. All right, the current and the loop, they're in the same direction. So which means that there's going to be a voltage drop right there. So it's I times R2. So that's our voltage drop. And then finally, we're here. All right, so the loop points from negative towards the positive. Okay, just want to make sure we're recording this. And so, which means that there's a voltage gain right there. All right, so that's your voltage gain. All right, so everything is going to add up to 0. The reason why everything adds up to 0, because the amount of voltage drop and the amount of voltage gain